All right, let's get started. Thank you for coming to Build. Thank you for taking the time to come to this session. My name is Vamshi. This is Jason. We're going to spend the next 60 minutes talking about the Azure Storage Blobs service, which is the object storage service for Azure. I'm going to give you first a brief introduction to Azure Storage and the other services that we offer as well, give you an overview of Blob Storage, and then really just kind of get into the key concepts, the architectural details, the internals of Blob Storage, and how you can build something to scale. We're also going to talk about what's new, do a bunch of demos showing off those new functionalities, and talk about proven practices and patterns to get to that scale, a petabyte scale, millions of transactions per second off of our service. So you've probably seen this slide a bunch of times. It's the number of regions that Azure is in. We're over 1 million servers today. The connection to Azure Storage is that Azure Storage is in every one of these regions. It's a foundational building block of Azure. Every Azure service that's built above us stores data in Azure Storage in some way or the other, directly or indirectly. So you're using Azure Storage even if you're not coding to it. In addition, if you're using Microsoft services like Office 365, OneDrive, Xbox, or Skype, you're using Azure Storage underneath the covers. You're using the Blob service, you're using the table service, you're using the queue service. As well, if you're using IaaS VMs at all on our platform, you're using Azure Storage for your disks and files. We also like to talk about hyperscale. So what that means for our service is in the next 60 minutes for this talk, we will have a net new 6 billion objects in our store. We will do over 48 billion transactions in this hour, and we will ingress and egress about 2 petabytes of data from our platform worldwide. Putting that in a different perspective, that's 13 million transactions a second. And over a year, we will be ingressing and egressing 17.5 exabytes from our service. And those numbers are going to go up because that rate of growth is also accelerating over time. We're also open. What do we mean by that? We have a REST API, of course, but all the client libraries we build to make programming against Azure Storage easier are all open source. They're all on GitHub. Our development team makes all the changes to those front-facing libraries in public. And we'd love to take contributions if you go there and find something that you want to change. We have client libraries in a number of different platforms. The obvious ones, .NET, Java, C++, but also Python, Ruby, PHP. And for the mobile platforms, we have iOS libraries, Android, and a Xamarin library as well. We also kind of focus on having a good hybrid story. With Windows Server 2016 shipping at Azure Stack, there will be 100% API consistent implementations of blobs, tables, and queues in Azure Stack. So you can write your code, have it run on-premise in your Azure Stack servers, on our public cloud with a hoster in a particular country, or wherever you need to do without any changes in your code. So what services do we offer? We've been sort of giving you these terms. For developers, we offer 3 services: blobs, tables, and queues. Blobs are our object service. We'll talk a lot more about that. Tables are our NoSQL service. It's a high-scale, key-value NoSQL store, really optimized for key-value lookups. We have a great set of proven patterns and practices. That's what's in that book that you just received. So if you go through that and take a look at it, any questions, please post them to Stack Overflow or the MSDN forums. Our engineering team looks at those forums every single day. In addition to the developer services, we do have queues as well, which is really useful for inter-service and inter-service communication, so it's reliable queuing. For the IaaS VM scenarios, let's say you're running a Cassandra database, or you're running a SQL server, or you're running Exchange or SharePoint or something like that, we have disks, that is the block storage, the persistent block storage attached to VMs. And we have that in standard and premium flavors. The premium flavor allows for scale-up, high IOPS, low latency workloads. We also have a new offering called Files that GA'd in September last year that gives you shared storage for your VMs over the SMB protocol. That's also accessible from on-premise as long as your corporate firewall allows port 445 outbound. There's a lot more documentation on these services at our storage documentation site. So please take a look. Again, forums are a great way to get in touch with us outside these conferences. So let's dive into Azure Blob Storage and talk about what it is and some high-level concepts there. So as I was saying, it's sort of the object storage platform for all of Azure. Right? It's where you would, by default, store unstructured data in our platform. So you have any application, you have any web service that needs persistent data, this is the most efficient, scalable, and cost-efficient platform to put your data in. Things that we can, typical scenarios include sort of apps, web scale data, but also things like big data from IoT, from genomics and other fields, healthcare, insurance, financial services, and more, as well as sort of the traditional workloads like backups and archiving, not only for you as developers to upload these things, but also we work with a wide variety of partners to have those products plug into our object storage platform. The key features of the blob storage service, you can scale to petabytes of data. We have many customers that store over a petabyte of data on our platform for their needs. We're very durable. We've never lost anybody's data in the years that we've been operating, so we don't assign a large number of nines to it because our aspiration is to never lose your data. You can choose your levels of durability as well. You can have locally redundant storage that's 3 copies strongly consistent in a single data center. Zone redundant spreads those things across multiple facilities in the same region. And we have geo-redundant storage with just a single checkbox. You can have async geo-replication to another region at least 300 miles away and protects you from regional disasters. In terms of availability, we have a 3 nines SLA, and we have 4 nines for reads if you're using the GRS product and have the read access copy of it enabled. One of the key features of our platform is that we're strongly consistent by default. So you always get read after write consistency, and we have good support for the different concurrency methods when you're dealing with multiple writers. So we'll talk a little bit more about that as we get into the details. We also take care of scale up and scale down for serving this data for you. So as long as you pick the right layout of data in your solution, we will observe the read and write rates coming into that data set and correctly scale up to thousands of servers or scale down when we don't need that capacity. That's sort of included in that price. You don't have to worry about it. You don't have to do a lot more in terms of giving us hints other than just designing your data correctly. And lastly, it is cost effective, right? LRS data is the retail price is about 2.4 cents gigabyte. So let's look at a couple of concepts here in terms of how blobs are laid out. Let's start with our favorite company for Microsoft, Contoso, and the Azure Cloud. Contoso has a set of subscriptions. Many of you who use Azure are familiar with these constructs, and they're sort of the billing construct for all of your compute, storage, and other things. Every subscription can have one-to-end subscription and storage accounts, and every storage account can have one-to-end containers. There's no limit on the number of containers you can have, and each container consists of many blobs, right? So this is sort of that structure you see when you look at a URI for storage. You have the storage account name in there, .blob.core.windows.net allows us to make it a fully qualified domain name, and /container/blob. There are 3 kinds of blobs that we have on our platform. The first kind is block blobs. These are the typical types of blobs that you use for object storage. So all your documents, images, video, mobile uploads, whatever, typically would go to block blobs. They can either be stored as single files for small files, or for larger files, you would store the blob as a series of blocks, and we'll go through how you can upload and download each of these. We also added a new kind of blob last year called append blobs. that allow you to do very efficient appending to the end of a blob for logging, for any kind of scenarios that need multi-writer append scenarios and things like that. So big data analytics is another scenario where you sort of have that scatter gather and you put stuff into an append blob. It looks the same, it's just that the append blob only allows appends to the end of that blob. The third kind of blob that we have is what we call page blobs. These are essentially large sparse files that need to be 512 byte aligned, right? So the data pages that you store in there need to be 512 byte padded. The advantage you get is you can read and write randomly anywhere in that page blob. This is actually what we use to build our disks products. So when you're using an IaaS VM and you're using disks, every disk is a page blob underneath the covers. So we built that for disks, and we said, hey, this is kind of a cool programming paradigm for some kind of scenarios directly for customers as well. For example, databases is a good one that comes to mind, where you can go really lay out pages in your blob the way you would like to. So let's take a deep dive into block blobs, that first kind of blobs, which would be the typical object storage functionality that you would use. I'm going to start with the demo where I show you some code. So let me switch over to that machine. But first of all, let's start with Azure.com, right? One of the most challenging things when you start with a new platform is, where's my getting started, right? How do I navigate this more? Lots of links, lots of tabs, blah, 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 right? So we always suggest starting with resources. We added this new thing called samples. If you go in here, as that comes up, you'll end up sort of coming to this drop-down with a set of products and a set of platforms. All the Azure services have a listing here that have developer scenarios. Let's choose storage, of course. And you get a set of code samples. You can also choose the platform you're trying to code against. So let's say we choose Java. That'll filter down to a set of samples. We're going to continue to build these samples out. We just started building these out early this year. But the idea here is no matter which service you want to go to in Azure, you come here, you get started, and you kind of get a very quick sample, very quick samples of patterns and things like that that you can go immediately start looking at, adapting for your needs. So do take a look at that. So let's take a look. I want to go through sort of a quick getting started sample. One of the things, we would typically do this in Visual Studio with .NET. One of the things we want to do here is sort of show our multi-platform story. So I'm going to open up Visual Studio Code. If you haven't used this editor, it's an awesome editor. It runs on Windows, Linux, and Mac from the Visual Studio team. And I've loaded up a sample that's written in Python, right? So let me go ahead and just click Go. You'll notice that the IDE, with an extension, has inline debug support, breakpoints, all of that good stuff, right? So let's go ahead and step through this code. We're importing a bunch of modules. And then we get into the storage code. The first thing you'll notice is we have an account name and an account key. We'll talk a little bit more about delegated authorization patterns, and putting your key in your code is not a good idea. But we will kind of go through that. For simplicity's sake, we have that here. Let's continue stepping over. And we get into the, okay, there we go, we hit that breakpoint. We have a file that we want to upload, and we look at creating first a block blob service object and configuring it with the account credentials that we want to go to. We create a container, right, on that account, and we then upload the blob. You can see that the blob, these calls are very, very straightforward. Create container, create blob from path, things like that. What I'm also going to do then is list all the blobs in that container. I finished uploading it. And you can see that that's the blob we just uploaded. We can go ahead and download the blob again just to make sure we get it. and we can finally clean up and delete the blob, right? So very straightforward, so obviously a very simple example, but the idea here is that you can get started with these simple samples, walk your way through our object hierarchy in different languages with the different client libraries that we have, and then build in on whatever platform you need to build in. So let's go through a little bit more detail about what blobs are, how do you name them, how do you structure them, how do you upload and download them, right? So let's start with a URI. So you have here an account name, foo. That account name needs to be a certain length and lowercase only. You also have a container name, which is the first thing after the slash. And that is also 3 to 63 characters lowercase. I'm throwing these out because when you get started, usually the first thing that trips people, developers up, is they try a container name. We all use camel casing or Hungarian notation, and we go, wait, I can't create a container with that. It's lowercase only. The reason we have these funky rules is because we have to adhere to RFCs for HTTP headers and things like that. So that's where those limitations come from. And lastly, you have a blob name. One of the things you'll notice is the blob name is actually 2016/January/Hanukkah, right? The idea here is that that whole thing is a single blob name, but we do support virtual directories within that. And we allow you to enumerate across these virtual directories, but it is actually a single blob name. There is no directory structure underneath the container. The container is think of it as a top-level directory. Everything else is just a convenience feature inside the blob name. In fact, slash is the commonly used thing, but we allow any delimiter that you want. You can pick your own delimiter that works for you. So let's look at the blob structure as well. The first thing that you have in there are a set of standard properties, the blob type. You have a couple of properties like etag and last modified timestamp that helps with optimistic concurrency. You have the length of the blob, of course, and you have the MD5 checksum, so you can always do data integrity validation anywhere along the way. You can also have a set of user-defined metadata up to 8 kilobytes of name-value pairs. So if you need to store a little bit of structured metadata with your blob, you can store that in there, and you can query that separately. So if you do need to do a little bit of housekeeping, storing stuff in there, you have the ability to do that. You can also set that metadata on containers as well, which is nice if you're trying to decorate the container with some metadata for, let's say, if you're storing image data and you want to put something about the images in there. There are no partial updates. This is a little bit of a gotcha. You have to retrieve the metadata and set it. This is a normal thing that happens. You kind of set a new name value pair. You assume it's additive. It's not. It's a retrieve and then set operation. And finally, you have the blob data itself. Today, you can have up to 200 gigabytes per block blob. For page blobs, it's a terabyte. So let's look at uploading block blobs. I have an image. It's less than 64 meg, and I want to upload it. It's very simple. It's one call, right? That's what we did in the sample. Put blob, and it goes away. Goes up to the cloud, right? So I'm obviously using pseudocode there as we walk through these examples. This only works if your blob is less than 64 megabytes. You can put it in a single put. You can get it back. A new put blob call will completely overwrite the existing blob. If you use an existing name, we'll just overwrite it. But the cool thing is if you're dealing with large block blobs, you get some more functionality. But let's start by looking at how do you upload these large blobs to start with. I want this blob in the cloud. It's about a gig file, let's say a movie. The first thing I have to do is chunk this blob into a number of blocks, up to 4 MB per block, and up to 50,000 blocks per blob. I have to assign each block an ID. Each of these blocks can be different sizes, so they don't have to be a fixed size. And then I call putBlock, the putBlock REST API call, to upload the data. I can upload these blocks in parallel. I can upload them out of order, so I can do some very efficient things around retry, continuation, and parallel uploads and downloads, right? So all of this is happening. The block itself is actually not yet materialized in the cloud until you call this call, the putBlock list call. So the putBlock list coalesces, it composes the blob out of all of the blocks that you've just uploaded, which is why you can do it in any order. because you're finally going to specify the order and the list of blocks that make up that blob, right? So that's kind of what's happening here. One little gotcha there, the block ID, while the blocks can be whatever size you want up to 4 meg, the block ID has to be a constant length base 64 encoded string. So pick that block ID if you're using it. If you want to use block IDs later, pick that wisely. We talked about the benefits, the continuation, retry, parallel uploads. You can upload large blobs very, very quickly with this method. But the blob upload also gives you some interesting functionality, especially around modifying block blobs. One of the cool things on our platform that isn't on the other cloud platforms is the ability to have blobs be mutable, block blobs be mutable. And the way we do that, let's take a look at this example. So let's say I have a block blob consisting of 5 blocks. Internally, it's actually stored in what we call a committed block list, okay? So when you did that put block list, that list of blocks gets stored into a committed block list. Let's say you do a new put block call, right? You can put a totally new block ID. You can also, and that starts accumulating in what's called an uncommitted block list, but you can also put block IDs, blocks, with the same block ID as an existing one. So I've just added a block 003, even though that exists in the committed block list. I can add another one. I can add another one. I can even add an overwrite the same block ID again. If you do that, the last writer wins in this case. So when we commit these and coalesce these blocks, the last one that you wrote in that uncommitted block list will win. So we have these uncommitted blocks. We want to compose our block blob, and that's how we make it mutable. The nice thing is you can kind of pick and choose what you want from this list of committed, uncommitted for put block list. So in this example, I'm choosing an uncommitted block list. So I'm updating block 2. I'm choosing the existing block 1. I'm choosing block 4, and notice that the last writer won there. And I'm choosing block 6, and I'm going ahead and committing it. The other neat thing is I can actually specify block 001 or any number of times inside that blob, and that works just fine. So you'll see that block 001 there repeats twice. That's actually allowed, so it allows you to do very efficient dedupe-based uploads if you want to do that. When you call that list, you now get a new block blob. Notice that block 001 occurs twice in this materialized block blob. Notice also that we've thrown away a bunch of blocks, right? So block 005 is now deleted and it's gone. When you make that call to put block list, that's when we discard all the unreferenced blocks in your block blob. You can call get block list is another API to get both of these lists at any point during these operations. The uncommitted block list is actually, we hang on to it for 7 days after you upload blobs. So if you decide to go on holiday and come back and then put it, it'll still be there if you have a short holiday. So nice features here. Blobs are mutable. You can modify and delete blocks. So if you think of this as if you're storing a set of record data or something, and you have records of varying length, you can actually store them quite efficiently in block blobs and only change the portion of the block you need. You can also only download the portion of the block you need, even with this sort of reference thing, okay? And the duplicate data thing is quite useful in terms of getting just sort of data dedupe if you were trying to do some kind of data dedupe on your end. Let's look quickly at downloading and copying blobs. For get blob, you can return the full, a normal get blob returns the full blob, including all the metadata and the properties, and the checksums allow you to do integrity validation. But the nice thing is you can do range reads. So you can say, here, get me this offset and this amount of bytes from that offset, which is nice. That allows you to build very, highly parallel downloading of blobs as well. So you can kind of go in and say, give me ranges. You don't have to know about block IDs if you don't want to, by the way. You can say, I don't need to know about blocks. I just need to download ranges of my bytes. We also have copy blob. Copy blob by default is a full copy. All the uncommitted blobs and blocks and snapshots are not moved over. Copies can complete asynchronously, so that's an important thing to keep in mind. When you call copy blob, you might get back a copy ID that says, okay, we've got you, we'll go ahead and do that copy later. and you can query for the status of that copy. Within an account, copies are very fast. Across accounts, they can take longer. And the nice thing about Copy Blob is you can actually copy from any external source that is accessible with a certain common set of HTTP headers. So for example, many websites do return those headers, as well as S3. So if you're trying to move data over, you can just do a copy blob and we'll asynchronously copy it over into our platform. Let's look at listing and deleting blobs. Listing operations, it's a container level operation, so you have to provide that container. We'll list them up to 5,000 at a time. We'll give you a next marker so you can page through that list. We do support filtering, so you can provide a prefix with the list blobs call, so you can say essentially get a begins with operation search, right, for your blob names. You can also traverse these virtual directory structures we talked about by providing the delimiter for those virtual directories, and we'll return a list of things you can supply back as prefixes. So you can say my delimiter is /, you'll get back a list of the virtual directories up to that first /. You can then go in and say, here's that prefix, please give me all the blobs that match that prefix. That's a good way of traversing these directories. Delete blob is very straightforward. I frankly put it on there because I felt sorry for delete blob. We always leave it out. One thing I'll call out there is if you have a lot of blobs, please consider using delete container. It's an atomic operation, so if you need to dump 1 million blobs, and you need to do that regularly, put these things in a container so you don't have to call delete blob 1 million times. All right. So you're probably looking at all of this going, holy cow, do I have to deal with all of this stuff for my code? And the good news is you don't. The client libraries take care of all of this for you and give you a very nice object hierarchy and object model to work with blobs. All these features we talked about, the automatic chunking into blocks, parallel uploads, retry policies on failure, all of that is implemented in every one of our client libraries. So you can sort of ignore all of this stuff that you just learned and say use blobs and know that internally that's what we're doing for you. It's nice to know these things, though, that way when something goes wrong, you can say, what actually happened here? As you start looking at your trace logs, you can see what we were trying to do underneath the covers for you. Let me touch on a couple of other advanced features as well for blobs. The first one is versioning. We support versioning through what we call snapshots and an API called snapshot blob. It gives you a read-only copy of a blob at a point in time, right? And that point in time is what allows you to specify that snapshot. So you have a date time stamp now that you can go get that snapshot. You can list snapshots, of course. You don't have to keep knowledge of that date time stamp. These snapshots can be read, of course. They can be copied or they can be deleted. You can use copy blob to make a writable new copy. So if you have a snapshot and you want to copy that over to a new blob and make it writable, you can. You can restore a snapshot over the existing blob by calling copy blob to a blob of the same name. That's how you promote a snapshot up and make it the new version, the current version again. And snapshots, however, the one thing is if you're doing normal copy blob from one blob to another, the snapshots are not copied. You can always copy a snapshot, but they're not all copied over for you to a new blob. And deletion of blobs requires you to delete all the snapshots. So that's a common failure. You'll call delete blob, it won't go away. You'll get an error, and that's because you have snapshots associated with that blob. Another feature I want to touch on is concurrency. So with concurrency, with our strong consistency, we actually allow you to do all the kinds of concurrency, both optimistic and pessimistic. So let's talk through those. Optimistic concurrency is when you have sort of optimistic locking, right? You want to know, hey, update this if nobody else has updated it, right? That's sort of the optimistic concurrency model. We support two things. We have a last modified timestamp that we update for you. So you can provide a timestamp and say, either if it's modified since then or if it's unmodified since then, go ahead and update it. We also have this notion of a thing called an E tag that changes every time there's a commit to the blob. So you can say if match that E tag, then. So that's an even more explicit thing of if this is the version of the blob that I got, you get that E tag back every time you retrieve the blob, then update it, otherwise don't. Conditional operations are supported on a number of the REST calls we looked at. If you look at the documentation, you'll see which ones work. We also support pessimistic concurrency with leases. So you can get exclusive access to blobs for when you need that locking semantics. The API is called lease blob. You can get exclusive write and delete access. You can either set it on a timer and keep renewing it, or you can get an infinite lease. If you do get an infinite lease and go away, you can always break the lease, of course, if you have the right credentials. You can also change the lease ID, which is kind of cool, to sort of have this workflow and have acquisition of the lock, kind of cascade down that workflow. And you can also acquire this on containers, which is nice. So if you want to lock the whole container and change stuff underneath, you can do that. Okay? And finally, we, of course, support last rider wins, which isn't much of a concurrency strategy. But if you know your data is structured that way, it certainly does work. Okay? A few more links there for documentation. So let's cover scaling really quickly. And to do this, I want to give you a quick overview of storage architecture. We have a stream layer, a distributed file system layer, that deals with all of our committing of data, dealing with disk failures, node failures, all of that. So that's one layer. There's a layer above that that actually implements these abstractions of blobs, tables, queues, deals with that load balancing, dynamic scaling, all of that. It's the serving layer. And we have a front-end layer that's our front door for request handling. So partitions are something that are implemented at that partition layer. It's the most important concept for you to scale your data, and partition keys are determined by you. For the blobs, it's your account name plus your container name plus your blob name. In the case of blobs, every single blob is an independent partition. So why that matters is a partition is served by a single server. So every single blob at the limit can be served by a different server from our system if you're operating at that load. But a server also serves many partitions. So that's something to keep in mind in terms of blob naming. Your container and blob naming is very important. Bias to prefixes if you can. So having unique prefixes at the beginning of that container name or blob name will allow us to spread you more quickly in case of load. And finally, scale targets exist because it provides isolation because we're a multi-tenant system. So for a single blob, our limit is 60 megabytes per second. And at an account level across many blobs, you can do up to half a petabyte of data, 20K TPS, and about 20 gigabits of ingress, 30 gigabits of egress. And that really allows us to kind of compartmentalize different customers and make sure we can still serve all of you efficiently. So that's about all I had in terms of internals of blobs. Some of these concepts will be better illustrated through the second half of this talk. But let's quickly run through then what's new on our platform. We've been pretty busy over the last 12 months in 2015. We GA'd 2 brand new services unrelated to blobs, the Azure Premium Disk Service and the Azure File Service. For blobs themselves, we talked about append blobs. We'll talk about shared access signatures, some of the improvements we've made there. We released a bunch of client-side encryption, client-side libraries, including client-side encryption, integrated with Key Vault to make that easy for you. So what's coming up soon? We're going to continue investing in client libraries. We've been making significant changes to our existing Python library. We're releasing a Xamarin and an iOS library. We're very pleased to announce that we're finally adding encryption at rest to our platform for blobs. So Jason will talk quite a bit more about that. We're also launching a new service. We are calling it Cool Storage. And this is a service that's meant for infrequently used data. And the way we implemented it is by creating this new blob storage account type to put blobs in. That blob storage account type has 2 tiers. It basically has a hot tier for commonly used data, which maps to the current blobs implementation, and a cool tier for that rarely used data. The API is 100% identical between these, which is nice. So all the stuff I talked about right now works fine with your cool storage account or the cool storage tier. So any code you have existing that works against blobs will just work against the cool tier. The durability options are the same. You can use LRS, GRS, or RAGRS. The availability is a little bit lower for cool. It's 2 nines instead of 3 nines, and it's an extra 9 when you have the geo-replicated storage and secondary reads. The pricing there is really what is changed. It's sort of pricing to match your workload. You would use the hot tier if you're going to make a lot of reads and writes against that data, and you need the access prices to be lower in exchange for a higher gigabyte per gigabyte price. The cool tier flips that and says, we'll give you a very low per gigabyte price, but then we'll charge you for access to that data because you know that you're not accessing that data very frequently. So you come out much further ahead, storing a lot of data in the cool tier and accessing it infrequently. So that's the big change. This will go live over the next few weeks. It's already making its way through our public cloud and getting deployed out there. So you'll be able to use it very soon. The tier switch from hot to cool is an account level switch. So you can actually just go into the portal and say, this whole account is cool data. I just want to switch it, right? You will be charged if you switch from cool to hot, but there's nothing to go from hot to cool. All right, so with that, I'm going to turn it over to my colleague, Jason, who's going to walk you through a number of different blob storage scenarios and design patterns.
Fantastic, thank you. Before we jump into detail, we thought it might be fun to take a scenario, build an application, and demonstrate some of the concepts that Vamshi's just described, as well as some of the patterns that we're going to talk about. So what we have here are two different mobile devices, an iOS device and an Android device. You can imagine the application being sort of an insurance assessor who's going on premises to actually determine an injury or potentially take some photos of a car that's been in an accident, something like that. So what they want to do is actually enter some details about the customer and then take a photo. Let's see how this works. The bright lights aren't going to help at all. Let's see if we can get something here. Take the photo. I think that worked very well.
You have an iOS device and an Android device.
That actually did not work.
I think it's uploading, Jason.
I think it's uploading. So while that's uploading, one of the things, the Wi-Fi here for the wireless devices has been terrible, so we'll give that a couple of seconds to upload. Why do we choose a mobile application? Mobile applications are interesting because at the surface they look super simple. But the fact is there's a lot of challenges you have to think about when you're building a mobile application, one of which is there's lots and lots of different types of devices. And that's where Xamarin's, I think everybody's seen all of the announcements. It's a fantastic platform for building mobile apps that span different platforms. And we've got full support for Xamarin, and we'll walk through that in a second. The second challenge, of course, is that mobile applications have limited local storage. So for recording things like images, videos, those sorts of things, Blob storage provides a perfect repository for the data. Now, if you're uploading data from a mobile application, you obviously don't want to store the user ID and password that you're using to connect to your cloud storage on the device because it's very easy to actually reverse engineer the actual application. So you want to think about how to use a delegated authorization mechanism. And we'll talk more about that shortly because you've got these untrusted devices. The next point is you've probably got a lot of these devices. You've probably got a lot of people in the field that are going to be out there using it. So you want to make sure that the platform can scale as your application's needs scale. And then lastly, you've got personal data here. So you want to make sure that for compliance reasons, you probably want to make sure that the data is encrypted. So that's where with the new encryption at rest capability, you can literally just enable it on the storage account and all of the encryption is taken care of for you. Find the clicker. All right, so what I'm going to do right now is just walk you through a brief Xamarin project. So again, Xamarin's an acquisition that we made recently that allows you to build mobile apps that run on Android, Windows phones, and Apple phones. When you create a new Xamarin project inside Visual Studio, you can also use, they've got their own editor as well. But when you create a new project within Xamarin, 3 different projects are actually created. The first one is what's called the portable class library. This is code that's actually portable across all languages. So it's written in .NET. It's basically your business logic. It's where you will typically interact with storage, those sorts of things. It's also where Xamarin has their own user interface definition language or framework called Xamarin Forms, which actually is an abstraction over all the different types of devices, user interfaces. So it means you don't have to build 3 different forms for 3 different types of applications. Xamarin does all that work for you. But there are cases where there's device-specific logic that you have to actually code against. Probably the best example of that is the camera. Each of the devices have a different camera, so there's different set of APIs that you have to interact with. So let's take a very quick look at the code. The solution I'm walking through, by the way, we'll have uploaded on that sample site next week sometime. So that's why don't worry too much about the code. Inside the actual Xamarin, the Android code here, there's basically 2 things going on. The first is when the application starts on an Android device, the very first thing it does is initialize a class called app which is actually our portable class. That's where all of our business logic resides. And it passes in a pointer to a method called upload picture. So this is the device-specific code that gets run when you click the upload button. Let's take a quick look at the actual the portable class library. This is the business logic code that's the same across all of the devices. You can see here, Vamshi sort of talked about the actual, we have this concept of a storage account, which we're basically creating a storage account class. We basically then create a blob, which allows us to upload a blob. So we've initialized those variables. Then we've got basically, I was a little bit lazy. I didn't actually create the forms. I've just done it through code. So I've created a button for uploading the picture. I've got a sort of on-click event, those sorts of things. A bunch of sort of UI logic. You can actually see the form here is basically a content page following a stack layout. So I've got all of the controls just lined up. Honestly, the form's not the most interesting part of this demo. There's basically, there were two buttons on the phone, one of which was to create a new account. If you're on a new customer site, you want to make sure all of that customer's data in its own container. So that's why with the blob proxy class that we've actually created, the client, I can then just call this very simple API, which is create if not exists. So within a storage account, it will then create a new container for each customer. If the container already exists, so be it. Once you've done that, we then click the actual button to take the photo, which is basically the on button, the sort of click event here. And what we're doing here is we're actually calling this method that was actually passed as input into this application. It was basically a pointer to a method that's actually device specific. So that's where we come over to the upload picture API. We then use either the Android or the iOS specific APIs for retrieving an object. And then at which point we basically take the actual images as captured, return a stream back to our common library, at which point we take the stream and we basically call our upload APIs right here. So we take the stream, which is provided, and then we basically, now we're creating a blob. We do that through actually this thing called a get blob reference, at which point we just do upload from stream. And we basically automatically store it in storage. Very simple. So hopefully, if you haven't really played with or explored Xamarin, definitely worth taking a look. The next thing we get asked frequently is, that's great, I've uploaded a bunch of data to the cloud. How do I actually see it? With file systems, you're used to sort of using File Explorer, something along those lines. The Visual Studio teams actually created, just like they've created the Visual Studio Code, which was the free code-based editor, which runs on 3 different platforms. We've now got a File Explorer. So if you go to storageexplorer.com, there's a free storage explorer that runs on Linux, runs on Mac, and it runs on PCs. So I can actually then I log in with my subscription. I can actually then see all of the different containers that exist within this one storage account. We'll actually see if the image from the phones, we should see here. Let's grab one of them. And you can see in the bottom there, it's actually downloading. So again, that's storageexplorer.com. You can download that. Again, bandwidth has been a little bit tricky. I'll come back to that. I'll show you that in a second. Let's go back to the presentation. Is it clicker? All right, so that was sort of one example of how blob storage can be used. There's obviously lots and lots of other examples, and for that reason, we've got lots of different client libraries. We actually have 12 different libraries that we've built to actually make sure that we meet all of your mobile, your web services, big data needs, and so forth. All of the libraries include the same sort of patterns that Vamshi was talking about earlier, and so forth. All right, now what I want to do is actually drill into a couple of patterns that are actually worth being aware of. Actually, let me just go back to this demo quickly. Still trying to retrieve that object. All right, so the first one is data movement. So again, one of the things that you want to do is if you're actually trying to move to this cloud-based storage, how do you get the data to storage? So one of the first things that we built was a tool called AZ Copy. So AZ Copy runs from the command line, but it's been designed to actually perform very efficient file copies. It can actually copy millions of files. It works out how to parallelize based on all of the resources available to your computer and send them as fast as possible. Similarly, if you've got very large files, it works how to actually split the file up into blocks and parallelize the uploading. It also includes journaling. So if you're in the middle of copying a million files, if you have a failure sort of halfway through, you lose network connectivity, your server reboots, something terrible like that, it's got a journal that can restart. It's useful for blob storage, table storage, and file storage. One of the questions we kept getting then was, it's great, I've got this command line tool, but I'm a developer, I want some APIs, help me write applications for things like backup, or I've got some specific needs that AZ Copy doesn't meet. So we actually took the core internals from AZ Copy and we created an open source library called the Data Movement Library, which actually allows you as developers to actually program against the data movement libraries. We'll take a quick look at that right now. And that is actually not the correct image. That's an image from earlier today, but it shows that the image was, or an image was uploaded. Let's go to the next demo, which is Data Movement Library. So again, Data Movement Library, it's built on top of the .NET Storage Client Library. It's available as a NuGet package. It's also available in source code. What we're doing here right now, we're actually talking, rather than using a storage account key to connect to the storage services, using a SAS token, which is our means of actually providing delegated access to storage. We'll talk a little bit more about that in a second. In terms of the class model, you can see the class model aligns very similarly with the taxonomy that Vamshi described earlier. If you're interacting with cloud storage, you basically create a cloud storage account. From that, you can create a blob client. The blob client then allows you to look at, if you want to create a container, which is what we're going to do if we're uploading all the data, you can create the container. Actually, you know what I might just do is while we're getting started, I've actually compiled this executable just to show you how it works. So this simple application that I've written, just because it also with the network not been great, I'm just going to actually run it right now. What I'm going to do is basically code, and I'm going to create. So what this is doing is it's taking all of the contents of the C::code directory and it's going to upload it to a container called code. For kicks, let's also start another one, which is going to actually take all of the content that's inside the demo folder and upload it to a directory called containers. So this is also going to show you, in addition to each of the processes being able to parallelize, you can obviously run multiple instances of the code at the same time. So that's running in the background. So back to the code. So basically, we worked out how to connect. We created a container. The next thing we want to do is obviously upload data. And the data basically, if you remember up here is where I was getting the information for the folder name and so forth. So let's take a look inside this method. Go to method. Extremely simple API. This basically, the class that you call to actually perform the upload is essentially transfer manager, upload directory async. Before you call that, there's a couple of configuration options you can set. The first is whether you want to actually perform a recursive copy or not, i.e. whether you want to traverse all of the underlying folders, the type of object that you want to actually copy. You can also provide filtering. If there's a specific content type or a specific file name convention that you want to look for, you can specify those as well. You can also specify the number of threads that you want to use. By default, it's 8 threads per core, but if you want to customize it for some reason, you can. There's also some events that you can tap into, which is what I'm using to actually write the output to the console. And then you basically start the upload. So there you've got sort of programmatic access to Data Movement Library, the same framework that powers AZ Copy. So we'll leave that copying running in the background. We will take a look at a couple more slides. One of the key sort of patterns, if you are actually doing any sort of data movement that I talked about, was if you're copying lots and lots of objects, don't worry about breaking the objects up and parallelizing. Just parallelize the objects. If you're copying very large objects, then obviously try to break them into blocks and parallelize that way. That way you'll get sort of maximum throughput. We did the demo. Delegated authorization. So we touched on this. Storage Platform actually has 3 different models for authentication and authorization. On the management plane, which is where you perform operations like creating a storage account, deleting a storage account, rotating your keys, those sorts of things, we support full RBAC because we're based on the ARM stack. So within the management portal, or if you're using any of our SRP, the storage resource provider APIs, we've got RBAC support. So meaning you can actually have users within your AAD instance with certain access to some of the APIs. On the data plane, however, which is where most of the applications are interacting, there's 2 different strategies for interacting with data. You're typically interacting with data at scale and extremely low latency scenarios. So in that case, we've got 2 different strategies. One is using a storage account key, which you can think about as essentially a user ID and a password. it's got full administrative rights. You can read all of the data in the storage account, you can delete all of the data. So in general, we don't recommend it to be your means of accessing storage from within applications. Really what we recommend you do is actually use what's called a shared access signature. The shared access signature is created using your storage account key, but then you issue it to applications. The shared access signature token allows you to actually delegate a subset of rights, for example, read only or read and write, but not delete. It allows you to actually specify very granular permissions at an object level, at a container level, at a storage account level, even for a complete service, either sort of tables or blobs or queues, something along those lines. The great thing about SaaS tokens, though, is that you can actually access the storage directly from your devices. So you don't have to build a data access layer like you would sort of in a SQL scenario. For IoT, for mobile devices, they interact directly with storage using a SaaS token that's been issued. And it's basically just a very, very scalable approach to actually managing your applications. I'll show you quickly what's involved in generating a SaaS token. It's extremely simple. I believe we have an example in here somewhere. So in this example, the token generator is actually running in process. Realistically, what you should have is a separate process or a separate service that your application is authenticating against using whatever means you've standardized on within your organization, and then you'd be issued the token. The API that you use is shared access account policy. It allows you to define a set of permissions. It allows you to actually define which service it is that you're interacting with, and whether you want service level, object level, or container level sort of granularity. You can also specify a period of time for which the SaaS token's valid. Could be hours, could be days, could be weeks. And that's sort of like the simplest way to actually perform delegated access. For mobile device scenarios, Microsoft has a mobile services framework that already has a SaaS token issuer built into it. So if you're building a mobile service, that capability is already provided for you. Two other, so there's actually 3 new features we've added to SaaS tokens recently. One was you've now got what we call account SaaS. So it's now account-wide scope can actually be managed within a SaaS token. So this is great for things like storage explorers and so forth, where in the past we had much more sort of granular level of permission, so you couldn't actually allow your employees to use a storage explorer just using a SaaS token. So we've broadened the scope of it to using something called account SaaS. Secondly, we've added 2 extra configurations. One is you can actually specify if the SaaS token can only be used on HTTPS. So this is very useful if you want to prevent users from accidentally sending confidential data over sort of HTTP. You can issue a SaaS token that will actually fail if it goes over HTTP. Secondly, for external access, i.e. external access outside of Azure, if you're coming from a static IP address, you can also specify an IP address that must be where the actual message originates from. So that's delegated authorization. I've actually touched on this a little bit, which is because the storage platform has blobs that are mutable, one of the scenarios we kept seeing customers trying to do was this sort of logging or audit type data where you're basically trying to actually append data constantly to the end of a block. The problem is for this scenario, you're typically doing lots and lots of very small appends. So if you have to do a get block list, put block list, it's not only inefficient, it's 3 REST calls. It's also really tricky to actually manage with concurrency with a large number of different clients trying to actually get the block list. So that's why we built, probably about 4 months ago, we've released something called append blob, which is a variant of a block blob that actually allows you to simply just, in a single REST call, append to the end of a blob up to 4 megabytes of data. So it's extremely useful in these sort of concurrent scenarios where you've got lots and lots of writers appending to the end concurrently. We've also, one of the other things that came up for audit data, people didn't want the clients to be able to delete or modify data that was already existing, so that's why it's actually impossible to actually modify data that's written to an append blob. So there's basically, you can also, if you want to prevent the actual client from deleting, make sure that the SaaS token that you issue to the clients only has an append permission, not delete or create. So what we'll do is the application that's running in the background, copying all that data from my storage account, from my code directory. The other thing that we actually built into this application was some basic logging functionality. So you can see basically the logging functionality is very simple. You basically, from your block client, you basically just call append blob. with a stream or with a text, whatever you want to log. We're logging right now to the $root container, and we should see the append log. Let's see, this one should be a much smaller file, so actually I notice it's getting a bit bigger now. It's been running for a while. So because we've got concurrent writers, within the log what we're logging is we've got the actual timestamp at which the data was logged. We've also got the process ID and the thread ID. So that way you should be able to see simultaneous writes to the log file without any concurrency issues. Again, we'll come back to that in a second, just the network's been less than optimal. A couple of things to be aware of with append blob. With multiple writers, there is a scenario where if a request is sent to storage, we persist the data, we perform the append operation, but the response coming back to the client gets disrupted for some reason. It's possible that the client may not be aware of what the final outcome is. The client library will see that the network connection failed on the response, and it will retry, meaning it is possible that you would actually have duplicate data in your append log. The same append operation could get called multiple times. So one of the things you want to do within your application then is have some way to be indicated, some way to be notified, within the append operation, have sort of a message ID or something like that, so you can actually tell if it's duplicate data. For single writer scenarios, you can actually specify the offset at which the append should occur, and if that offset's no longer valid, then the operation will fail. So you can actually detect if duplicate failures have occurred. It happens very rarely, but for audit data, it's potentially important for you to actually have that capability. All right, the audit logs finally opened up. So what we can see is, again, for each of the operations that were performed by data movement libraries copy, I've got the actual time at which the operation occurred. I guess my logs are actually getting quite long now, so we can get to the bottom here. And you can basically see here, there's basically the process ID from the two different processes and the different threads and the actual file that they've copied. So, great example of how to actually use the append blob functionality. While we're in here, we've got data movement library running in the background. We should see a couple of new containers opened up, one of which was code, and one of which was demo. So these are these console apps that are just running in the background, basically copying all of the data up. And what you can see here is basically, I created a different container for both of these data movement library jobs. We're looking at the actual demo container right now, which if we went to my file system, it's probably pretty messy, you'd actually see, I can't spell, obviously. Basically, there's a number of different folders there. And we've basically got the notion of this Storage Explorer tool basically shows the different folders and the different code and so forth that's in the folders, and it's basically copying it up for us. So it's very easy to actually build those applications for yourself. One of the things I will remark is within the code, because we've got these 64 different threads and each different process right into the console, we had to write some basic, we've got a mutex controlling how the output is written to the console, which is slowing the output, the operation down a little bit. But you obviously wouldn't do that if that was a production app. So we talked about multi-append. The next new capability, which I believe everybody should be extremely excited about, was about a year ago we announced we had client library encryption, which allows you to encrypt data within your applications. The challenge was that you have to modify your applications, then you have to manage your keys, and customers were saying it's great for some scenarios, but I just want my data encrypted. So that's why we've just announced Blob Storage Service Encryption. It's literally a setting that you specify in your storage account, and from then on, any data that you upload will automatically be encrypted at rest for you. So let's take a very quick look at how to actually enable that. Right now we're in preview. We're in one region right now, which is East Asia. Over the next few weeks, we'll start rolling out across more regions. Probably within about 6 weeks, we'll have deployed the capability worldwide. So if we went into, in this case, we've got this build 2016 storage account, just from the portal. If we go across here, we can see there's a new menu option called encryption. And scroll over here. So an explanation of what the technology does. Because it's in preview, there's a short sort of questionnaire you have to fill in. You complete that, and then we'll allow you access to the capability during the preview program. What about a round of applause? That's one of the most asked for features. Come on. Extremely simple, though, to use. So that was sort of what we aimed for there. While I'm in here, there's one other feature that I wanted to quickly demonstrate as well. I've actually mentioned cool storage. This is the other feature that's also worthy of a round of applause, but I won't ask you to do it twice. Okay. What we can do now, we actually have these two different pricing models. We have the cool model, which is currently what this is enabled for, and the actual the hard model. So again, if you're storing some data that you're going to access infrequently, all you have to do is go into storage account, mark it as sort of cool storage, and you basically the price for storage goes down significantly. Yeah, I think we talked about encryption at rest. All right, another feature that gets asked for a lot is, hey, I've uploaded all this data to blob storage. Now I want to search it. How do I search it? So we've worked closely with the Azure search team. So they've now actually got the ability to actually allow you to actually ingest and index and search storage containers. So they can also take a PDF, they can take Office documents, XML documents, so forth, crack them apart and have them be indexed as well. So that's something that we've seen a lot of people asking for. It's in public preview. If you're interested in the same capability being available for table storage, please send that alias an email, because we've sort of built the technology out and we just want to make sure that we understand the usage scenarios before we release that. So,
all right. So just to wrap things up, blob storage is a service that is highly scalable, available, and durable. You've sort of seen the evidence for that. It's secure now with the encryption at rest, just a one-click operation. And we're open and multi-platform, as you've seen through all the demos with Python, with Xamarin, and others. The hybrid support is coming with Azure Stack with Windows Server 2016. And the cool storage really enables a new cost-effective tier for storing large volumes of rarely accessed data. You can look more at Channel 9, we have different talks that go into other services, our documentation. Please do take some time to fill out the survey for this talk. We really appreciate your feedback. We look at that and look at how we can improve our talks, our demos. So that's the QR code. Please take a minute to fill that survey out. If you have the paper survey, please drop it to us or on your way out the door. We will be outside answering questions. We'll be there as long as you need us. So thank you so much.
Thank you.